Hello everyone, this is Shashwat Sharma. In the following few minutes, we'll learn about the CFD of Kaplan Turbine. We'll also learn what is the importance of performing CFD of a turbine, and what models to use, and what results to expect. Hydropower plants generate 1/5 of the total electrical power produced in world. Even a small improvement of the hydrodynamic design and efficiency can contribute a great deal to the supply of the electric power. The efficiency of a hydropower plant depends on a number of parameters such as turbine efficiency, draft tube efficiency, and generator efficiency. Turbine blades have been found to have an efficiency loss due to the runner losses. A small increase in performance in these power stations represents a considerable economic value. This work will analyze the flow field in the runner blades. This analysis is based on CFD simulations. Runner is the most important component of the turbine, and its blade profile is designed at different sections from hub to casing to get the best performance and efficiency. The rotation of the runner and operation of the turbine, either below or above the rated conditions, cause variation of flow parameters from hub to tip. Hence, actual flow pattern in turbine space deviates from the simplifying assumptions made in designs, thus affecting the turbine performance. The experimental testing of turbine models at different operating regimes on specifically designed test rigs is the conventional approach to assess the performance, but it's expensive and time consuming. Therefore, the numerical procedure in CFD is of highest importance. Let's just start with the introduction. The Kaplan turbine is a propeller type water turbine which has adjustable blades. Developed in 1913 by the Austrian professor Victor Kaplan, the turbine consists of automatically adjusted propeller blades with automatically adjusted wicket gates to achieve efficiency over a wide range of flow and water level. Its invention allowed efficient water production in low head applications that was not possible with Francis turbines. The head ranges from 10 to 70 meters and the output from 5 to 200 megawatt. Runner diameters are between 2 and 11 meters. The range of turbine rotation is from 79 to 429 rpm. The CFD of the blades can be used to plot the velocity profile around the blades and thus predicting the flow rate versus efficiency graph. This can be used to design a more efficient design of the turbine without actually having to manufacture a prototype. The problem is modeled as turbulent and assuming an incompressible flow. We use the Reynolds average Navier-Stokes equation to solve the problem. The K-epsilon realizable enhanced model is used. Now coming to the question, why do we use K-epsilon realizable model? We use it as it is more accurate and has improved equation for epsilon. Also, it has variable coefficient of turbulent viscosity instead of a constant. Moreover, it has been proved that it has improved performance for the flows that involves the following. First, boundary layers under strong adverse pressure gradients or separation. Second, rotation and recirculation. Third, strong streamline curvature. Moreover, we will also be looking at some coefficients that will be helpful in plotting graphs after the simulation is over, like pressure coefficient, velocity coefficient, flow deflection, total head utilized by the runner, and hydraulic efficiency. The right hand side figure shows the computational domain of a single runner blade, and the left hand side shows the compilation of all such domains together. Looking at the pictorial representation of velocity from CFD results. First picture shows us velocity streamlines at the hub showing vortex forming at the suction side of the blade near the tailing edge where the low pressure region is created. Second picture shows us velocity streamlines at the shroud showing the water flow path at the blade clearance. The third picture represents the velocity streamlines on the pressure surface of blade, indicating the path of water flow over the pressure side. Coming to the fourth picture, it represents the velocity streamlines at the suction surface of the blade where the vortexes occur, and it is very clear at the velocity vector. Now coming to the graphical representation of the results of the CFD simulation. The first figure shows the pressure variation from inlet to outlet. This means that the pressure decreases from inlet to the leading edge and then increases at the leading edge. After that, it decreases gradually along the blade until it reaches the tailing edge and then increases to leave with the atmospheric pressure. The second figure shows the variation of the velocity component from inlet to outlet along the streamline. The velocity component u in x direction, starting from small value near to 0, increases gradually along the streamline in radial direction of the blade. The velocity component v in y direction starts from a large negative value and increases gradually along the streamline and stops at the value a little less than 0. This velocity is in the direction of the blade span. The velocity component w in z direction is semi-constant along the streamline. This is in the direction of rotation. The total velocity decreases from inlet to outlet due to rotation, swirling, and the occurrence of the vortices. Figures show the performance curve of the blade under different operating conditions. This indicates that the efficiency of the turbine blade increases with the increase of RPM until it reaches a maximum point and then decreases gradually. The power also increases with the increase of RPM to a maximum and then decreases gradually. Thus we conclude that to extract maximum performance by a turbine, we should use it at the rated conditions only. We learned that the CFD is a powerful tool in the modern turbine engineering. It saves time, money, and human labor and gives pretty accurate results. It can be used to perform little changes in the design and predict the resulting performance of the turbine. That will be all for now. Thank you and have a nice day.